Have you ever paused to think about the invisible components that make our modern world actually work? Talk about the hidden complexities in things we use and see every day. You know, like a massive bridge or a skyscraper, or even just the frame of your car. We often look at the finished thing, right? But we rarely consider the microscopic science happening at every single weld seam, or the vital materials that get used up in the process itself. These are what we call consumables. And in welding, believe me, they are far more sophisticated and, frankly, critical than you might ever imagine. Okay, let's unpack this a bit. Today, we're taking a deep dive into two really fundamental welding processes, and we're looking at the unsung heroes that make them work. The consumables for submerged arc welding, or SAW, and Flux-Cored Arc Welding, known as FCAW.
That's exactly it. And when we talk about consumables for SAW and FCAW, we really mean everything that's, well, consumed or used up to create that vital weld. So that includes the electrode wires, the fluxes, even shielding gases sometimes. What's really critical to grasp here is that their precise size, their specific type, their condition when they arrive, and maybe most importantly, how they are stored. All of these factors are absolutely vital for the final weld's quality and, its structural integrity. If you overlook any of these details, it can lead to pretty serious long-term consequences down the line.
And our mission today is really to cut through the technical jargon, pull out the most important nuggets from the source material you've shared with us. We want to offer you, our listener, a kind of shortcut to understanding these specialized consumables. And hopefully we'll share some surprising facts and essential insights along the way that might make you look at a weld and maybe the world around you a little differently. Okay, first up, let's talk about submerged arc welding, or SAW. This is a process you often see used for really heavy-duty, high-production welds. Think shipbuilding, pressure vessels, that kind of thing. When we look at SAW consumables, we're primarily focused on two things: the electrode wire and the flux. So let's start by peeling back the layers on those wires. What are we looking at?
Right. The electrode wires used in SAW are generally very high quality. They have to be. For common carbon manganese steels, they're typically graded by their increasing carbon and manganese content. That dictates their strength, essentially. For other alloy steels, the grading is more about their precise chemical composition, tailored for specific properties like heat resistance or corrosion resistance. And these wires, they come in various forms to suit different production scales. You can find them on coils, maybe around 25 kilograms, or on larger reels, about 300 kilos. And even massive drums holding roughly 450 kilograms for really continuous, heavy-duty work. They can be either solid wires, just solid metal, or in some specialized cases, metal cord wires, which have some powder inside. Now, what's really ingenious here, I think, is the thin copper coating you often find on carbon and low alloy wires. It looks simple, maybe just decorative, but this coating, it serves three absolutely crucial functions. Firstly, it ensures excellent electrical contact right at the contact tip. That's vital for a stable, consistent arc.
Okay, like ensuring a good connection, basically.
Exactly. Think of it like plugging something in properly. Secondly, it provides a super smooth wire feed. It reduces friction inside the liner that guides the wire, and as a bonus, that significantly cuts down wear on the contact tube itself.
So it protects the equipment too.
Precisely. And thirdly, it offers protection against corrosion, rust, while the wire's in storage. So it's not just a pretty coating, it's a really meticulously engineered detail. It underpins the stability and quality of the whole process, and that's why keeping these wires really clean, free from any oil or dust, is so important. These wires are incredibly versatile too. You see them used in everything from pipelines to heavy machinery. They can weld carbon steels, low alloy steels, creep-resisting steels.
Right, and you mentioned creep-resisting steels. Just to quickly clarify for our listeners, those are for high-temperature jobs, yeah? Where metal might deform over time.
Exactly. Perfect example. They're engineered to maintain their strength and shape under prolonged stress at high temperatures. Think power plants, certain chemical processing facilities, maybe even jet engines. They literally resist creeping or deforming under that long-term heat and load. So yeah, also stainless steels, nickel-based alloys, even special alloys for surfacing applications.
Fascinating. So we've got the wires covered, from their clever copper coating to their wide range of uses. But in SAW, the wire, as you said, is only half the equation. The flux, that's where things get really dynamic. It's not just a passive covering. It's an active player in actually creating the weld. What exactly does it do? And why are there different kinds?
You're absolutely right. The flux is far more than just a simple covering. It has multiple vital roles in SOLU. First off, it shields the molten weld pool from the atmosphere. That prevents contamination from oxygen and nitrogen, which could seriously weaken the weld. It also actively cleans the weld pool, removing impurities, like a little chemical scrub. And crucially, it can actually modify the chemical composition of the weld metal itself.
Oh, really? So it adds elements.
It can add or sometimes help remove elements to tailor the final properties. Plus, it prevents heat from escaping too quickly from the welding zone. That ensures the weld cools at the right rate, which affects its structure, and it influences the shape of the weld bead, what we call its wetting action. Now, when it comes to the types of fluxes, there are two main categories, and they have really distinct manufacturing processes and implications for the weld. You've got fused fluxes and agglomerated fluxes. Imagine making glass that's kind of analogous to how fused fluxes are made. Their components are dry mixed, then melted at incredibly high temperatures. We're talking over 1,000 degrees Celsius. After melting, they're cooled rapidly, maybe shot through water or poured onto chilled blocks. This produces these hard, reflective, irregularly shaped particles. You literally cannot crush them in your hand.
Wow, okay. Hard stuff.
Yeah. And because of that high temperature process, it's actually impossible to incorporate certain heat-sensitive alloying compounds, like ferromanganese. They'd just be destroyed. Fused fluxes tend to be acidic in nature, and while they're quite tolerant of, say, poor surface conditions and generally easy to use, they produce a good weld contour, and the slag, the glassy layer left after welding, is usually easily detachable, but they typically yield comparatively lower quality weld metal, particularly in terms of tensile strength and toughness.
Okay. So if they're harder, can't have certain alloys added and produce slightly lower quality welds. What's the upside? Why use them?
That's a really good question about the trade-offs, because their advantages are significant in other ways. They have good chemical homogeneity. That means their composition is very consistent throughout the batch. It's also easy to remove the fines, those tiny dust-like particles that can sometimes cause issues in feeding systems. And crucially, they are normally not hygroscopic.
Meaning they don't absorb moisture easily.
Exactly. They don't readily soak up moisture from the air, which makes storing them much, much simpler. They can also be readily recycled without major changes in their composition. So, for applications where maybe ease of use, good slag detachability, and especially moisture resistance are the top priorities, fused fluxes are a really strong choice, even with that trade-off in certain mechanical properties. Now, in contrast, you have agglomerated fluxes. They're made quite differently. Think more like making, a pelletized animal feed or a granular fertilizer. Powdered components are dry mixed, then they're bonded together with some kind of binder like sodium silicate or potassium silicate. They're pelletized and then baked at a much lower temperature, significantly less than the 1,000 degrees Celsius. Then they're broken up and screened. These granules are typically dull, generally roundish, and they are friable.
Friable
meaning they're easily crushed in your hand, you can crumble them. And they can even be colored for identification. Now, because of that lower manufacturing temperature, many different agents and compounds can be added during production. This allows for much finer control over the final weld chemistry. Agglomerated fluxes tend to be basic, chemically speaking, and they generally produce weld metal of improved quality, better strength and toughness. However, this often comes at the expense of usability. They tend to be less tolerant of poor surface conditions like rust or mill scale, and they generally produce a slag that is much more difficult to detach and remove after welding. It can be quite sticky.
So it sounds like agglomerated fluxes are the way to go if you absolutely need that top-tier strength and toughness, but you kind of pay for it with more hassle during the actual welding and cleanup. Is that right?
No, you've absolutely hit the nail on the head. That's the core trade-off. Their big advantages include the easy addition of deoxidizers and alloying elements, giving you really precise control over weld properties. They can also generally be used with thicker layers of flux during welding. The disadvantages, though, are pretty significant. As we touched on, they have a strong tendency to absorb moisture. This is a big one. Moisture pickup can lead to hydrogen getting into the weld, causing potential cracking, or gas evolution from the molten slag, which causes porosity, little bubbles trapped in the weld.
Right, and porosity is a major defect.
Huge defect. I've personally seen big projects face serious delays and very costly rework simply because the agglomerated flux wasn't stored properly and picked up moisture. There's also the possibility of changes in the flux composition over time due to segregation, where heavier particles settle, or the removal of fine particles if they're not handled correctly. It's also worth mentioning that sometimes two or more different fluxes can be mixed together for specific operations, trying to get the best of both worlds. But this really comes with its own set of challenges, mainly segregation during storage and feeding. This can lead to real inconsistencies in the weld. It's like, mixing sand and gravel over time. They separate, and your mix isn't uniform anymore.
Right.
So if we tie this all together, the final properties of the weld metal, whether we're looking at tensile strength, elongation, toughness, the temperature it was tested at, these are all a direct result of using a particular wire with a particular flux in a particular welding sequence. This synergy is absolutely paramount. It cannot be overstated. It's absolutely critical that all CSWIP consumables, both the wires and the fluxes, are stored in a dry, humidity-free atmosphere. You have to strictly follow the manufacturer's instructions to minimize any moisture pickup. And rule number 1, different types of fluxes should never be mixed unless it's a specific controlled blend recommended by the manufacturer. And one of the sort of unsung heroes in ensuring all this happens correctly are the classification systems. Standards like BSEN ISO 14171 or the American AWS A5.17. These are essential tools. They help welders and engineers identify these complex combinations by providing specific values for tensile and impact properties, the flux type, fused, agglomerated, basic, acidic, etc., and the wire's chemical composition. This ensures that the right consumable combination is selected for the specific job, guaranteeing performance, integrity, and preventing potentially disastrous mistakes down the line. It's like a blueprint for predictable results.
That makes perfect sense. So, okay, we've established just how crucial those external fluxes are for FCAW. They act as a shield, an active chemical agent. But what if you could essentially bake all that critical chemistry, all those active ingredients, right into the wire itself? That seems to be the ingenious approach of Flux-Cored Arc Welding, or FCAW. It feels like a completely different philosophy, doesn't it? How we get those necessary materials into the weld pool.
It absolutely is a different philosophy, and a very clever one at that. An FCAW wire is essentially a metallic sheath. Think of it like a thin, continuous metal tube that's filled with a powdered core. The metallic sheath, the outer tube, has two main jobs. It provides form stability to the wire so it can be fed smoothly through the welding done without collapsing. And it serves as the current transfer medium during welding, carrying the electricity down to the arc. But the real magic, as you said, the powerhouse, is that filling powder inside the core. This powder is a true multifunctional marvel. It does several things simultaneously. It helps stabilize the arc. It adds crucial alloying elements to tailor the weld metal's properties. It produces a gaseous shield to protect the molten pool from the atmosphere.
So it creates its own gas shield, like MIG welding.
Some types do, yes, they're called self-shielded. Others require an additional external shielding gas, similar to MIG bag welding. Those are called gas shielded. The core contributes significantly either way. The powder also forms a protective slag covering over the cooling weld. And it can even include iron powder simply to increase productivity, basically adding more metal into the weld faster.
Wow. So this inner powder is potentially doing everything the external flux does in SAW, plus adding alloys, plus maybe generating its own shield, plus boosting productivity. That is quite the multitasker packed into a thin wire. What are some of the key elements they actually put into that powder? What specific jobs do they do?
Exactly. It's highly concentrated precision chemistry. The power in that powder comes down to specific core elements and their functions. For instance, you'll almost always find silicon and aluminum in there. Their main job is deoxidizing and denitrifying the weld, which means they effectively scavenge or grab onto any harmful oxygen and nitrogen impurities, which, if left in the weld, could cause brittleness or porosity.
Okay, so they're like little cleaners.
Precisely. Then you have elements like manganese, molybdenum, and carbon. These are typically added to increase the hardness and strength of the final weld metal. Nickel is another common one. It's great because it improves a whole range of properties: hardness, strength, toughness, especially at low temperatures, and importantly, corrosion resistance. And finally, you often find elements like potassium and sodium compounds. These are vital for stabilizing the arc itself, making it smooth and consistent, and they also help form the necessary protective slag layer after the weld solidifies. Each ingredient has a specific purpose, carefully balanced to ensure the final weld has exactly the properties needed for its application.
This brings up a really important point, I think. Given how much complex chemistry is packed inside these wires, the way they're actually manufactured must surely create distinct types, right? And presumably, these different manufacturing methods would lead to different pros and cons, especially concerning something as critical as moisture sensitivity, which you highlighted with SAW fluxes. What are these different types of FCW wire construction, and what's the practical impact for the user?
That's a great point because the manufacturing process directly impacts the wire's characteristics and, crucially, how you need to handle and store it. Broadly speaking, we have three main types of cord wire construction. First, there's seamless cord wire. This type is formed from a single piece of sheet metal that's shaped into a tube and welded shut, and then drawn down to size, making it truly sealed. The huge advantage here is that it is not sensitive to moisture pickup. This makes storage much less of a concern compared to other types. It can also be copper-coated, just like solid wires, for better current transfer and feeding. And it generally has a relatively thick sheath, which makes it quite robust and good for standard two-roll drive feeding systems. The main downside: it's significantly more difficult and therefore more expensive to manufacture.
Okay, so seamless is the premium option, basically. Less worry about moisture. What else?
Right. Second, we have butt joint cord wire. This is made from a strip of metal that's bent around the core powder, and the edges are simply brought together, butted up against each other, maybe with a slight weld or seal. This type offers pretty good resistance to moisture pickup, though perhaps not quite as foolproof as seamless. It can also be copper-coated. Like the seamless type, tends to have a fairly thick sheath. The potential issue is that it can sometimes be difficult to get a perfect seal along that butt joint during manufacturing, which could be a potential entry point for moisture over time. And finally, there's overlapping cord wire. This is probably the most common type you'll encounter, mainly because it's the easiest and cheapest to manufacture. It's made by forming a strip of sheet metal into a U shape, adding the flux powder, and then simply folding or overlapping the edges to close the tube.
So there's just a seam where the edges overlap.
Exactly. And the key characteristic here is that it is sensitive to moisture pickup because of that unsealed overlapping seam. This is a critical point for storage and handling. It also cannot be copper-coated because of the seam, and it typically has a thinner metallic sheath compared to the other two types. So it's the easy win for manufacturers in terms of cost, but it creates a potential headache for the end user regarding storage, especially in humid environments. The general manufacturing process for all of these, just briefly, involves forming those thin sheet metal strips, adding the carefully measured flux powder into the channel created, closing the wire somehow, seamless weld, butt joint, overlap, and then drawing the whole thing down through dies to its final precise diameter.
Right, so that moisture sensitivity and the overlapping cord wire, that really sounds like the biggest practical takeaway for users, doesn't it? It seems like you really, really need to control your storage environment with that type, or you're just asking for porosity problems in your weld.
Absolutely. That moisture sensitivity is probably the #1 operational concern with overlapping wire. It's a classic example of manufacturing simplicity leading to, well, user complexity, or at least user diligence. You absolutely need to control your storage environment. Keep the packaging intact until use. Avoid leaving spools exposed for long periods, especially in damp conditions. Otherwise, yeah, you're definitely risking hydrogen pickup or gas evolution from moisture in the flux, leading to porosity, which, as we know, can compromise the weld's integrity significantly. One key advantage, though, of flux-cored wires in general, compared to some other welding consumables like certain types of stick electrodes, SMAW, is that they typically do not require baking or drying in an oven before use.
That's handy.
It does simplify handling in many workshops, for sure. And just like with SAW, when it comes to selecting the right FCAW wire for a specific application, those classification standards are invaluable. Standards like BS-EN 18632 or the American AWS A5.20 are incredibly helpful. They provide really detailed information that helps users select the correct wire. They detail things like tensile strength and impact properties, any light alloy additions, the type of core, basic rutile, etc., whether it needs external shielding gas or is self-shielded. Also, the welding positions, it's suitable for, flat, horizontal, vertical, overhead, and even the expected level of diffusible hydrogen, which is absolutely crucial for preventing hydrogen-induced cracking when welding certain high-strength or thicker steels. It really ensures you're always picking the right tool for the specific job requirements.
So, okay, let's try and synthesize this. What does this all really mean? We've definitely unpacked some incredible intricacies in both SIW and FCAW consumables. From the precise chemistry baked into wires and fluxes to the manufacturing methods, the copper coatings, it's a surprisingly deep topic.
Yeah.
Far beyond just, a stick that melts or wire from a spool.
Absolutely. I think the most critical takeaway here is that these materials are absolutely not generic filler materials. They are highly engineered components. And understanding their specific characteristics, things like the subtle but crucial manufacturing differences between fused and agglomerated SIW fluxes, or the distinct properties and, importantly, the moisture sensitivities of seamless versus overlapping FCAW wires, understanding this is fundamental. It's crucial for achieving the precise weld properties you need, for ensuring safety and structural integrity, and ultimately for optimizing the overall performance and cost-effectiveness of the welding operation.
It really highlights that deeper level of understanding, doesn't it? The idea that every single choice, from the specific alloy element added to the wire's core to how dry that bag of soft flux is kept in the storeroom, it directly writes the script effectively for the final weld's strength, its toughness, its resistance to cracking, and its long-term reliability. It's really a testament to the depth of detail required in material science and engineering, even in something as seemingly straightforward as joining two pieces of metal together. So perhaps a final thought for you, our listener. Next time you encounter a structure, whether it's huge like a bridge or something smaller like industrial equipment, something that clearly relies on welding, take a moment to consider that unseen world of consumables that went into its creation. How might just one overlooked detail in a consumable specification sheet, or maybe a simple lapse in its storage procedure on site, potentially have a profound long-term impact on that structure's integrity and safety? And maybe think about how these principles, the importance of precise material selection, meticulous handling, understanding the why behind the specs, extend to countless other complex systems in our technological world, where often the smallest unseen component can dictate the success or failure of the entire enterprise.